Hello everyone, welcome to the 7th episode of this series. In this video, we'll learn about matrix multiplication. So last time we learned how to multiply a matrix and a vector, and this time we're going to learn how to multiply a matrix with another matrix. Okay, so matrix multiplication. So if you have two matrices A and B, the product AB is the matrix whose ijth entry is the dot product of the ith row of A and the jth column of B. So in more detail, if we want to compute the ijth entry of AB, so the entry in the ith row and the jth column, we take the ith row of A, the jth row of B, and then we multiply the corresponding entries and then add the results. It's very similar to how we multiplied a matrix and a vector. One thing to note is that the rows of A must be the same length as the columns of B. In other words, the width of the first matrix has to be the same as the height of the second matrix. If we look at the explicit formula, this is what it looks like. It's very similar to the matrix vector multiplication, as I said, because you can treat the second matrix as just a collection of column vectors. So we take the ith row in the left matrix and the jth column in the right matrix, and then we multiply the first entry to the first one, the second to the second one, and then so on, and then add them up. Let's look at an exercise. So we're given matrices A and B. So A is a 2 by 3 matrix and B is a 3 by 4 matrix. So the number of columns here, in other words, the width of A is 3 and the height of B is also 3, and therefore we can actually compute AB. So let's do so. So the entry at 1, 3, so in the first row and the third column is going to be 25 because to compute the entry at 1, 3, we take the first row in the left matrix and the third column in the second matrix. And then we take the corresponding entries, multiply them and add them together. So we multiply 3 with 6, minus 1 with 3, and 2 with 5. So we get 18 minus 3 plus 10, and that's 25. And then we plug in 25 at matrix coordinates 1, 3. Similarly, the entry at 2, 4 in this product matrix will involve a multiplication of the second row in the first matrix and the fourth column in the second matrix. So we do the same thing again. We get a 36, and we plug it. You plug it in the in the product matrix. So if you want, you can pause the video and compute the rest of the entries of AB, and you can verify that your answer looks like this 2 by 4 matrix here. Okay, so I've already said this before, that for AB to exist, for this product to make sense, the width of A needs to be the same as the height of B. In other words, the number of columns in A needs to be the same as the number of rows in B. And let's say that you already know the sizes of your two matrices. You can find the size of your product matrix as well. So if your A is an M by N matrix and your B is an N by P matrix, then your AB is going to be an M by P matrix. So essentially, if like the middle sizes are the same, you forget about them, and you can use the remaining sizes for the size of the product matrix. And as I've said before, if the middle dimensions do not agree, that will mean that the width of A is not the same as the height of B. In that case, the product cannot exist. Okay, so let's look at another problem. We're given two matrices A and B. A is a 2 by 3 matrix and B is a 3 by 2 matrix, and we want to compute the products AB and BA. So let's first compute AB, because A is, A is a 2 by 3 matrix and B is a 3 by 2 matrix. AB would be a 2 by 2 matrix because of the canceling we talked about on the last slide. And we compute these entries, one by one. So for the first entry, we take the first row of A and the first column of B. We multiply the corresponding entries, and then we add them up, and we get a 0. 2 minus 2 minus 0 is 0. And then we do the same for all the other entries. In this scenario, we get 0, 6, 2, 3. So this is a 2 by 2 matrix, and that's like the value of my matrix AB. In a similar fashion, we can compute BA. So because I'm starting with a 3 by 2 matrix and then multiplying it with a 2 by 3 matrix on the right, the product matrix will have size 3 by 3, again, because of the canceling concept. And when you compute it, you actually get a completely different matrix. 3, 4, 0, 2 minus 2 is 7, and 1, 0, 2. So what we just saw was that AB was not the same as VA. The matrices were different, their sizes were different. And in other words, the order in which we multiply matrices with each other is very crucial. So we say that, matrix multiplication is not always commutative. In fact, it is very rarely commutative. Like, it's very rare that you have matrices, such that when you multiply them in any order, you get the same answer. Okay, so I'm going to leave you guys, with a question. Is there a matrix that commutes with every other matrix of the same size? So think about it. Think about what matrix it could be. And if you get an answer, let me know. And with this, I would like to end this episode. I will see you guys in the next episode. Until then, happy learning.